Chapter 19, Electric Potential Energy and the Electric Potential. These two terms sound really similar, and it turns out they're closely connected. Just as in the last chapter, chapter 18, we saw that electric forces in the electric field, those ideas were also really closely connected. The main difference, once again, is going to be the charge. So let's charge into this. So we'll start out by talking in the first section about potential energy. And we're actually going to go back to 2a for a moment and imagine if you have a ball, that ball feels a force pulling it down towards the earth, right? Gravity pulls it down. And so you can calculate the potential energy the ball has at some height. And you could also calculate the potential energy at another height, and you could calculate the work done by gravity in moving from that height A to height B. And that would be equal to the change in gravitational potential energy, which here we've written as GPE. Previously, we just said PE for potential energy. The G is just for gravitational potential energy. So that's one example that we've already seen before. And it turns out our electric potential energy is very similar. So just as if you have a ball above the surface of the earth, it feels a force pulling it towards the earth. If you now have a positive test charge that is in between two charged plates, right, with a positive plate above, negative plate below, that test charge is going to feel a force pulling it down toward the negative plate. And so you can think of these two parallel examples, and it's a really helpful framework. So you want to try and keep that in mind when possible. And this test charge has a different potential energy at point A than at point B. So that's something else we could describe, the electric potential energy at point A versus point B, which point B is closer to where it wants to go, so it's a lower potential energy. And you could calculate, once again, the work done in moving from point A to point B, which will be positive because you are moving to a lower potential energy. You're moving in the direction that the charge wants to go. So this introduces the potential energy section. We'll come back to it a little bit more, but to introduce electric potential, we're going to divide each of these terms by the charge. So if we divide the work done in moving from A to B, the electric potential energy at A and the electric potential energy at B, all by the amount of charge Q0 present, then that gives us the potential energy per unit charge, which is defined as the electric potential, or oftentimes it's just referred to as the potential. The electric can sometimes be dropped. So this is our definition then of electric potential, or potential, that the electric potential at a given point is the electric potential energy of a small test charge divided by that test charge itself. So we can write this, the electric potential symbol is V, and we have our electric potential energy divided by the amount of test charge. Now, what is our SI unit of electric potential? Well, to think about that, we're going to think about our units for electric potential energy and that of the test charge. So what are our units for charge? For charge, it should be the coulomb, right? C. Now, electric potential energy. We haven't yet talked a whole lot about electric potential energy, but we've said it's similar to our previous potential energy, gravitational potential energy. So what is the unit if we're talking about potential energy? It's the joule, right? So electric potential energy is much the same. It has the units of joules. So the electric potential then is units of joules per coulomb. And this pops up so frequently that it's given another name. The joule per coulomb is also just called the volt, which has a capital V as a symbol. This gets a little confusing because electric potential symbol is V and the unit of it is also V. So hopefully that is not very much confusing, but in some ways it's simpler because it's just all V. All right, so that introduces the units of it. Now, what if we're looking at the electric potential difference between 2 points? Well, we could imagine doing that, right? VB minus VA, so the potential at B minus the potential at A, and that would be equal to the electric potential energy at B divided by Q naught minus the electric potential energy at A divided by Q naught, or going back to that original equation, negative the work done in moving from A to B divided by Q naught. And instead of writing out all of these terms, we could then use a delta. So VB minus VA, or V final minus V initial, is just delta V, the potential difference. It's equal to the change in electric potential energy divided by Q naught, which is negative the work done moving from A to B divided by Q naught. So this allows us to go back and forth between a change in potential energy and a change in potential. And one side note that's here is that the potential difference between 2 points is often called the voltage. This is something we're going to see once we get to chapter 20, and it can be really confusing, the two terms. For chapter 19, we're just going to focus on electric potential. But once you focus on potential differences, like between two terminals of a battery in chapter 20, that's something we'll be seeing a lot, it just gets called the voltage. So that's coming. And that's convenient because it matches the units of it. So it's often a bit simpler to use. Okay, so this introduces the electric potential. Let's check out an example of this so that we have a little more of an idea of how this all works. So we have work, potential energy, and electric potential. So the work done by the electric force as the test charge, plus 2 times 10 to the negative 6 coulombs, moves from A to B is 5 times 10 to the negative 5th joules. Find the difference in electric potential energy between these points and determine the potential difference between these points. All right, so the key here is we want to figure out what's been given to us. And units will really help us out there, right? They mentioned this test charge and some units of coulomb, so that suggests that that is going to be our Q naught. Now we also have this 5 times 10 to the negative 5th joules, great unit. What is that quantity? Well, that's hidden up here at the beginning. That's the work done by the electric force. So we can call that our work, AB, right? Now, what are we solving for? Well, we're trying to get the difference in electric potential energy, so delta EPE, and we're also trying to get the potential difference between 2 points, so that's our delta V. All right, so thinking about the last slide, we should be able to do this, right? Let's take a look. So we know that the work done in moving from A to B is related to EPEA minus EPEB. But if we want the change in electric potential energy, it will be that at B, the final, minus the initial A. And so that means we need the negative of it in order to get our work done, or to get the change in electric potential energy, it will be the negative of the work done. So EPEB minus EPA is negative work AB, so negative 5 times 10 to the negative 5th joules. Once we have that figured out, we know that the change in electric potential, or the electric potential difference, VB minus VA, is just negative of the work done in moving from A to B divided by Q naught. So we can take that negative 5 times 10 to the negative 5th and divide by 2 times 10 to the negative 6 coulombs, and we'd find that that is negative 25 volts. We could have just as easily done this with VB minus VA is equal to delta EPE, which is the answer we got in A, which is just the same thing, negative 5.0 times 10 to the negative 5th joules. We would still have had to divide by the test charge Q naught, but we'd get the same result. All right, so this introduces the idea of the electric potential, and I said that we want to think about the potential energy like the ball, and thinking about where the ball wants to go. So let's try a conceptual example to check our understanding of that. So the accelerations of positive and negative charges. A positive test charge is released from point A, shown below, and accelerates toward B. Upon reaching B, the test charge continues to accelerate towards C. Assuming that only motion along the line is possible, what will a negative test charge do when released from rest at B? So I want you to think about this before you move on. So come up with an answer. What is a negative test charge going to do when released from rest at B? And go ahead and pause the video now. Right, hoping you are ready to move on. So if we find out that the positive test charge is accelerating towards C, we know the negative test charge is going to do the opposite. It's going to want to accelerate towards A if it's released from rest at B, because negatives do the exact opposite. And this gives us a general rule as we're approaching these scenarios. And that's that a positive charge is going to accelerate from a region of higher potential toward a region of lower electric potential. The positive test charge is just like the ball, where it's going to accelerate towards a lower height, right? If you could start out at a higher height or a higher electric potential, it's going to naturally want to accelerate towards the lower electric potential, the lower height. Negative charge does just the opposite. So it's going to accelerate from a region of lower potential to one of higher potential. It wants to go to where the positive charges are. So negative charges are able to go uphill, if you will, while the positive charges will always roll downhill, the natural result. All right, this introduces the electric potential difference and electric potential energy. We're going to put the energy together in the next short video, taking a look at how we can add in all of these energy considerations.